These are the questions that were the hardest for people, so I thought I'd quickly review them before I get started. A myopic person sees that her contact lens prescription is minus 4.00 diopters. Which statement is correct? What does myopic mean? Okay, that means nearsighted. If a person is nearsighted, what do they have a problem with? Seeing far. So the prescription is going to tell us about the far point. So we can cross off those two because those are talking about the near point. Now, what's going on with the lens is it's taking an object at the ideal far point. What's the ideal far point? Infinity. So it's taking an object at infinity and making an image at the actual far point, except for one thing. It's making a virtual image, so the distance image is minus the far point. And so then we just use our thin lens equation, power, which is 1 over focal length, is equal to 1 over distance object plus 1 over distance image. Well, 1 over infinity is 0, so I'm just going to put 0 for that one. And so then distance image is equal to 1 over the power, and that's minus the far point from what we've written right there. And so that's going to be 1 divided by minus 4.00 diopters. Last thing is, what is the diopter? It's an inverse meter. And so that means I'm going to have an answer of equal to minus 0.250 meters, or minus 25 centimeters is minus the far point. Hence the answer was her far point is 25 centimeters. Less than a fourth of the students answered that one correctly. I thought it was very important to go over that one. The next one, a thin sheet of oil, gives you the index refraction, is floating on water. Show that the light coming from the air above the oil with normal incidences, blah, blah, blah. As I told you the day after the exam, there is a mistake in that equation. It turned out to really not make a difference in the grading because either people did it right or they didn't remember going over it in class. Now, I told you this was going to be on the test. This should have been no shock because I said you're going to have to do this on the test. But what you needed was air, oil, water, light comes in, and then we're looking at reflection, so I need to show the first two reflections. The first reflection is right here. The next reflection will go down, back, and out. So I need to compare those two reflections. Specify what thickness is here. This here is the thickness. And then I have to go through and calculate the phase shift that's occurred on each of the paths, because constructive interference or destructive interference is going to be depending on the difference in phase. So I'll calculate phase 1 is equal to, and that just had one reflection. Only one reflection for that light path. Well, with reflections, you have to consider, did it reflect off of something with a faster speed of light or a slower speed of light? So in this case, going from air to oil, does oil have a faster or a slower speed of light? Slower speed. Because the slower speed, there is no shift for the reflection, so the phase for that first one is 0. Now for the second one, it went through the oil twice, and so I have a path length that's going to be 2 times the thickness, but then I'm going to convert that into radians. So if it's 2 times the thickness, I need to define how many wavelengths was that, so I'll divide it by the wavelength. Well, I can divide it by the wavelength in oil and multiply it by 2 pi. So that's a lambda sub O, and then times 2 pi. That's the phase shift for the path. But then I also have to look at this reflection. Going from oil to water, did it reflect off something with a faster speed or a slower speed? Okay, here's the numbers. Water has an index refraction of 1.33 and oil 1.46. Is water faster or slower light speed than oil? Faster. In the faster, if you reflect off of a faster speed, then you have a phase shift of pi. And so that's the phase shift for the second one. Now I'm going to replace wavelength in oil is equal to wavelength in air. Oh boy, I should not put O for oil because that looks like the original wavelength. Oil. We use a subscript 0 for the wavelength in air divided by the index refraction of the oil. And so that would be so that's my phase for the two different paths. Now we're comparing the phase, and we have to use the condition for, and the problem asks, is it destructive or constructive? We have to use the condition for destructive interference. So the change in phase is equal to m plus 1/2 times 2 pi radians for destructive interference. And so now I take my change in phase and put in what I just worked out above. And you notice on the right-hand side, I distributed my m plus 1/2. And now I need to solve for thickness. So now we see where my error occurred. Subtract the pi's from both sides and they disappear. And then I'm going to divide everything by 2 n oil over lambda naught times 2 pi. And I end up with thickness equals m lambda 0 over 2 n oil. And so you see, was I looking for thickness? I probably wasn't looking for thickness, was I? No, I was looking for lambda. Okay, so let's go the other way. Shoot. Solving for lambda, I can divide everything by 2 pi m over lambda. And so now just canceling the 2 pi's, the m there, lambda there, and I have and so that's what the equation should have been. Now on this, I basically gave an extra point to everybody because if you did all the work right, you would get a different answer, and it's easy to make a mistake if you're looking for the wrong answer. The simple fact was that with this one, very, very few people even got as far as the picture. And so the fact that there was an error in the answer wasn't material, because if you didn't get the picture right, you can't do the rest of it. Rebecca?
Do you get our papers to follow?
Yes, you should get them this afternoon. That's what I was working on in my office while I came in here just at the time class started. Okay, so that's that one. That was one of the two that you knew was going to be on the test. The other one you knew was going to be on the test was the ray tracing one, which people did much better on, thankfully. Other two that were low performing. What's the principle used to derive both the law of reflections and Snell's law? What's the name of that principle? That is, what's the name of the principle? I could have had the names of the principles that says descriptions here. What principle did we use to derive Snell's law? Not talking to the three people in the calculus class where we did it a different way. Or not using that one. Huygens principle. Huygens principle that says each point on a wavefront can be treated as a point source. These other things, like and behave as either a wave or a particle. That's true. That's our wave-particle duality statement. Light works the same way forward and backward. That's also true. Nothing can travel faster than light in vacuum. That's also true. All those were true things, but only one of them was used to derive both the law of reflections and Snell's law. And then the last one was the geometry problem. I worked that out in class. We had it in a homework problem. It appears that people still weren't very strong on the geometry of that. So I'm not going to work that out right now, but that's the last of the problems that gave people real tough time on the test. We have another test tomorrow. The test tomorrow is going to be over chapters 28 through 30. And so we will start with a just review of the material that's going to be on the test. Question, Corso?
When are we going to know what we got on the test, or it's already up?
This afternoon. As I said, that's what I was working on just before class.
Do you know the class average?
I don't. I know the high score was 85%. And it's because this first one, or the second one, excuse me, that even though I told everyone it was going to be on the test, they still generally got it wrong. And then the myopic one, very few got right. Yes, Michaela.
Do you know how the polarizer question is graded?
The polarizer question, thankfully, most people had it right. And so they just got full credit for having it right. Right? There were a few people who, like, one person scribbled out the right work because they figured it was wrong. Well, I gave them full credit for it. Because they had the right work, and then they scribbled it out because they thought it was wrong. One person erased all of their work, and I still gave them only 1 point off because I figured maybe they had the right work. They shouldn't have erased it, because you can't know if they did it right or not. But I still gave them the benefit of the doubt there. Other than that, it was, once again, the fact that the answer was wrong really was immaterial. One person used sine instead of cosine because I guess without the right answer, and I just gave them credit because they were at that point, they'd done all the work right, and they're trying to figure out, how do I get this number? And so I tried to be generous there and give points as people would have had if it had been the right answer. But yes.
You heard in the test?
I don't think so. Like I said, the problems that people had an issue with, one of them, I told you specifically, this is going to be on the test. So, people should have been prepared. Excuse me?
You said it was 1 out of 8 equations. It wasn't specific.
Yeah, I said that's correct. I said you won't have the equation. You're going to have to do this on the test because there's 8 different variations. There's only 2 equations in the end, but there's 8 different variations.
It's personal opinion, but I think we should do problems like that before we take the test so that we know how it's doing.
And I did.
Instead of having it on a test and then everyone gets it wrong.
But I did model it in class. I did the entire problem in class before the test.
The old problem?
Yes, that problem exactly.
We did the graphic one.
Mhm. We did it. It was during the lab period when I was lecturing. But yeah, I did the exact problem.
Then how did everyone get it wrong?
Well, clearly people didn't understand what I was doing.
And there's no curve?
I don't think so, no. Because the problems that were missed were not ones that should have been missed. These are all things that we covered, I think, quite carefully in class. Okay, preparing for the test tomorrow. It's going to first start with relativity. Well, I mean, the chapters. So relativity, key things with relativity are your starting postulates. The speed of light in vacuum is the same in all reference frames. So, for instance, if you have a question that says, in this reference frame, this thing is going this fast, it turns on its headlights. In another reference frame, how fast does the light travel? You don't need to do any math because that first postulate tells you the speed of light in vacuum is going to be c in all reference frames. Second postulate, in an inertial reference frame, all of our laws of physics work the same. So you need to be able to identify, what is an inertial reference frame? A reference frame that is not accelerated. It's a reference frame where Newton's first law is correct. If Newton's first law is not correct, then it's not an inertial reference frame. That's why it's called inertial. Newton's first law is the law of inertia. So you have those postulates of relativity. Why do we have time dilation and length contraction? Well, understanding the why comes from, Einstein was just thinking, what would happen if? And he came up with his clock idea. And the clock, all of the physics says you have two different times per tick, depending on the reference frame. And then Einstein said, well, the laws of physics must be true, so it must be correct that you have two different times. That time is malleable. And so because of the travel, because of the different rates of travel, you actually have what we call warping of the space-time continuum. You have length is contracted, so always remember length is contracted, whereas time is dilated. And if you're going to do a problem that has to do with time dilation or length contraction, you need to be able to identify which reference frame is going to be the proper time, which reference frame is going to be the proper length. Now, some things that are easy to identify, if you know one of them is proper, the proper time is always, just look at the term time dilation, it's the shortest measurable time for the between events. Shortest time. So if I have a problem that says Richard measures the time between these events is 1 second, and Alex measures the time between these events is 3/4 of a second, which one is the proper time? With the assumption that one of them is proper, you can answer immediately which one's the proper time. Alex's, because it's the shorter one. Does that mean that Richard's is incorrect? No. Proper is not a synonym for correct here. Proper is telling us the one that is our reference that we can use to go to any other reference frame. Now, if it tells you Alex measures this, Richard measures this, and gives you speeds of Richard and Alex with respect to the object, or that it could be neither of us are the proper time, so you can't just bank on the shortest one as the proper one, because it could be there's another time that's even shorter that's the proper one. For length, it's just the opposite. Proper length is always the longest possible. So just the inverse rule. How do you determine if you don't have something that says one of these two is proper? How do you go through and determine if something is proper? For time, it's a proper time measurement if the clock is stationary with respect to the events. So for instance, my heart rate is going to have a proper time for the time between beats if it's a clock that's stationary with respect to my heart. So a clock that I'm taking with me is going to measure the proper time for the time between beats of my heart. If I'm running and you are measuring, say we have a device that flashes a light every time my heart beats, and you measure the time between flashes, you're going to be measuring a dilated time because you're measuring with something that's moving. Yeah.
So, okay, this proper time, it's like the shortest distance, but then time, sorry. Then why is it called time dilation? Wouldn't that be like?
Because the time gets
actually
bigger in other reference frames. In other reference frames, it's dilated, so bigger.
So like from space to here, pretty much our time is shorter, like traveling, but then on Earth it's longer? Or
Anything that you measure for yourself is going to be the proper time, which means it's the shortest time possible for that. So anyone observing you that sees you as moving is going to see your heart rate slow down. It's going to see you living a longer time. And so that's where the dilation is. Yes?
A couple minutes ago, before you started talking about length contraction, you were talking about how it's not always the shortest, the proper time is not always the shortest time, how like if two people were measuring two different objects, like how would you be able to understand?
Well, you only have the proper time if you're measuring for the same thing. Or excuse me, you only can compare if you're measuring for the same thing.
Okay, well, what was
Right, and so what I was saying is, for instance, if Richard measures the time between flashes of the light on that spacecraft to be this, and Alex measures it to be this, and it's going this fast with respect to Alex, how fast is it going with respect to Richard? And to determine that, I'd have to say, well, with respect to Alex, it's going this fast, and then calculate the proper time. And then for calculating the proper time for Alex's, the proper time would be shorter than what Alex measured. Then we can calculate speed relative to mean. Right? You don't have, when you're given times, you don't have to have one of them as the proper time, is the point. The proper time would be measured on that spacecraft of which neither Alex nor I were on. So neither of us is measuring the proper time. Amanda?
Did you just say you had to find the proper time for Alex's?
From Alex's.
So then you'd have proper time for you and then a proper time.
No, from, not for, from. From Alex's measurement, if we know how fast Alex is moving with respect to the object, then we can calculate the proper time by using Alex's information.
Okay.
And then using that proper time, we can calculate how fast I'm moving with respect to that object.
Okay.
But it's not the proper time for Alex, it's the proper time from Alex's measurements. Okay, proper length. Identifying the proper length is it's going to be the proper length if the thing you're measuring the distance for is stationary with respect to the measurer. So if you measure the length of a barn and you're standing on Earth, you're going to measure the proper length because the barn's stationary with respect to you. If you're flying by in a spacecraft, you're going to see that barn as contracted. Now, something that's important to keep in mind with length contraction is that length contraction is only in the direction parallel to the relative velocity. So if the spacecraft is heading straight down toward Earth, it's going to measure the normal width for the barn, but the height of the barn it will see as shortened. Because it's only in the direction parallel to its velocity that it's going to have the contracted length. So then understanding how to apply time dilation, length contraction, those equations are pretty simple. Obviously, they'll be given to you on the test. That the time difference between two events is equal to gamma times the proper time distance where gamma is defined as 1 over square root of 1 minus v squared over c squared. So I usually calculate gamma right at the beginning of a problem. Every now and then it'll turn out to be unnecessary, but usually it's necessary. So I just usually calculate right at the beginning. Length contraction. The length is equal to the proper length divided by gamma.
Did you say, so length contraction is only parallel, or is the length?
Yes, it's only parallel to the velocity. And then the final thing on relativity was, well, I don't have, you do need to know how to do addition of velocities. And while you'll have the equation there, just to make sure it's straight and clear in your mind, for addition of velocities, velocity AB is equal to velocity AC plus velocity CB over 1 plus velocity AC, velocity CB over C squared for parallel velocities, which is the only case you're going to have. You're not going to have perpendicular velocities, so don't worry about the perpendicular velocities. It's slightly different, well, it's a different equation. Notice the subscripts. The subscripts are of vital importance. We go way back to first semester at the very beginning. VAC or VAB. VAB is the velocity of object A with respect to reference frame B. VAC then is velocity of object A with respect to reference frame C. Your formalism needs to be like this, where you have the first one in what you're looking for is the first index, A in my case, is the first index in the first velocity. The second index in what I'm looking for, B in this case, is the second index in the second velocity. And then the inner indices, which in my example are C, have to be the same. So it could be VAC plus VCB or VAD plus VDB, as long as those inner ones are the same. And then on bottom, you have the same set of indices here as you have up here. So that's how you add the velocities. Now, relativistic momentum was gamma mv. A little bit different. Question?
So for the other, I remember you had a PowerPoint and had both this equation and another one.
Yes, we're not going to worry about the other one. Yeah.
Okay.
So relativistic momentum is a different equation, which means Newton's second law is a different thing than what you learned, because I taught you, a simplified version of Newton's second law. Newton's second law itself is unchanged, but Newton's second law is that net force is equal to dp dt. That's the true Newton's second law. The calculus students learned that, so they have no change in their Newton's second law. You learned an approximate form Well, that one we have to throw away because momentum is no longer mv, and that's based on the change in mv with respect to time is ma. But you still do have the other approximate form we learned, delta momentum over delta t. So you have to use this relationship for Newton's second law. And then finally, for energy, we learned a whole new thing. We learned that you have kinetic energy is equal to gamma minus 1 mc squared. Rest energy is equal to mc squared. And total energy is equal to gamma mc squared. So we have these new relations for energy. And so you may have to do something with those. And a last thing, the correspondence principle. The correspondence principle says that in regions of overlap, our new physics needs to agree with our classical physics. So regions of overlap in this case means at pedestrian speed. If something's going 1,000 meters per second, that's a pedestrian speed. Lots of molecules in this classroom are going 1,000 meters per second. And so at 1,000 meters per second, that kinetic energy needs to agree with our classical equation of 1/2 mv squared. And we saw that for small speeds, we have to use that binomial expansion for gamma. And indeed, for small speeds, it does all agree. This E equals mc squared, if I get to the actual new material part of the lecture, is going to be today's key. That's the key to nuclear energy right there. The rest energy is mc squared. Chapter 29 was looking at the particle nature of light. We had already studied the wave nature of light. We have phenomena that can only be explained by a wave nature. Polarization. Polarization can only exist if you have a transverse wave. It's not possible to have polarization of particles. Interference. Interference can only occur with waves. Diffraction, bending around, obstructions can only occur with waves. But Einstein said, what about this? The photoelectric effect, he showed, can only be explained if you have particles, each particle carrying an energy of hf. Energy for a photon is hf. Compton scattering. When you have a light wave scatter off of an electron, it shifts its wavelength, which means it shifts its frequency if you stay in the same material. And that's not possible with a wave. That can only occur if you have a photon with energy hf. X-rays. The X-rays are energy produced when you have electrons slowed down. Can only be explained if you have the energy of the photons is hf. And pair production, which we have not talked about yet. So pair production, don't worry about, that won't be on the test. So you should be able to do the calculations for Compton scattering. So you just have that equation that's the shift in wavelength is Compton wavelength times 1 minus cosine theta. That theory principle of complementarity that I talked about, once again, is going to apply here. We have two competing theories that have to complement each other. So when you have one phenomenon, maybe wave, one phenomenon, maybe particle, but they have to complement, they have to work together. Finally, for chapter 30, we had quantum mechanics. Quantum mechanics is looking at the wave-particle duality. At its fundamental, that's the Schrodinger approach, looking at the wave-particle duality. Treating electrons as waves is what we primarily do when we talk about this wave-particle duality. Does it have to be electrons? No, it does not. It could be any particle. But electrons is the common one because you're only going to really see the wave behavior if you have really small particles. So electrons are small particles, we see the wave behavior there. If you go to bigger things, even things like protons, it's much harder to see the wave behavior. So it's universally applicable, but usually applied to electrons. You should have these different models. The Democritus model, that is, that you just have indivisible pieces that he called atoms if you cut it down small enough. The plum pudding model, I haven't tried. The plum pudding model was the model that J.J. Thomson came up with after his cathode ray tube showed that you had electrons coming out of a piece of metal. The planetary model is the model that Rutherford came up with after the thin film experiment with gold. And then we have the Bohr model. I'm going to run out of highlighter colors here. The Bohr model, because the planetary model, failure of the plum pudding model was plum pudding model couldn't explain discrete energy levels and should have had the electrons couldn't explain discrete energy levels. It also couldn't explain how things could bounce off each other. The planetary model couldn't explain discrete energy levels, and it suggested that electrons should just fall in and you wouldn't have stable atoms. So the Bohr model makes its 4 statements that you have to have stationary states for electron orbits so that they can't just continuously fall in energy, that you had quantized angular momentum, that the energy of the absorption emission spectrum is equal to the energy jumps between the 2 levels. There's one more that escapes my mind. That was the Bohr model, but it couldn't explain things like the fine structure. Fine structure is, I'm going to go back to yellow. You're going to just have to deal with yellow again. Oh, that's not yellow, that's green. I also should work on my colors. That's yellow. The quantum model is the final model that explains everything as well as we understand it. So make sure, now the Bohr's calculations, that's, you have a particle going in a circle with angular momentum of L is equal to mvr is equal to n h bar, where h bar is h over 2 pi. And if you have something going in a circle, force of, in this case, electric field, sum of the forces toward the center is equal to mass v squared over r. And so you get that equation k z e squared over r squared equals mv squared over r. You should be able to go from that and the angular momentum quantization to getting a specific radius for the Bohr atom. I'm not going to ask you to go from there to the specific energy because I didn't do that step of the problem in class. Okay, last thing here, make sure you understand what the 4 quantum numbers are. So what does n tell you? What does L tell you? What does m sub L tell you? What does m sub s tell you? Understand what kinds of particles the Pauli exclusion principle applies to, because it doesn't apply to all particles. I'm going to lecture on that in quantum mechanics next hour if you care to come. Here are the actual technical reasons why it applies to fermions and not bosons. Yes?
It just applies to electrons, right?
No, it also applies to protons. It also applies to neutrons. It applies to any particle that has a 1/2 integer spin. So we call those as a group fermions, but that's the key. If they have 1/2 integer spins, then the Pauli exclusion principle applies. If they have integer spins like a photon has an integer spin, the Pauli exclusion principle doesn't apply. You can have all the photons all in the exact same energy state, all at the same quantum number. And so we do. Photons always come with a spin of 1. It's all. And Hund's rule, what's the basis for Hund's rule? That would be going back to Friday. Was it Friday or was it Wednesday? Wednesday? Well, Hund's rule is all about lower energy. You're going to fill lower energy states first. And it's lower energy to have the magnetic moments aligned than to have them anti-aligned. So you're going to start filling the orbitals. All of the electrons will have their angular momentum, their magnetic moments, in the same direction. And what do we call the orientation of the electron's magnetic moment? The spin, right? Okay, that's the review. Yes.
For the model part again, so how would you ask questions about that? Would you just be like, tell us what these models do, what they accept, what they don't accept?
I could describe a model and ask you which one it is. I could do a mix and match and have features of the different models and you match them. Could have, for one of the last problems, for you to, list the reasons for this model, reasons it was abandoned. All right, 10 minutes of new stuff. To how many people is this new? What is that? That's how we label nuclei. So if I have an atom is a nucleus with electrons. I'm using this to label the nuclei. I will put a charge state if I want to worry about the electrons, right? So A, Z, and N. A is the atomic mass. A is atomic mass. That's the number of protons plus neutrons. So I have right here A is atomic mass equals, and I'm going to put Z plus N because Z and N are defined elsewhere. Z is the atomic number, the number of protons. And N is the neutron number, the number of neutrons. So there's Z, there's N, there's A. So 3 numbers there. How many of those do I really need? 2. I only need 2, really. And in fact, what does X tell you? Which element it is. But the elements are defined by their atomic numbers. If it is molybdenum, it's always going to have 42 protons. The number of neutrons could vary. You have different what we call isotopes of molybdenum. But if it's molybdenum, it's always going to be 42. So anytime it says MO, bottom left corner is going to have 42. If it has MO and 41, that's a mistake. Right? Mistakes are made. So you really, if you have the symbol, you have Z. So if you have one of these things, you have the other. And then if you have this, you'll automatically know what that is, if you know what Z is. So oftentimes, we will only show the symbol and one number. So for instance, we'll talk about carbon-14. Technically, carbon-14 is that 12, 6. 6 plus 8 is 12, right? The 2 bottom numbers equal the top number. But we usually erase both of those and just put carbon-14. Or sometimes they'll write it as C-14. Because the carbon-12 tells us 6, and 14 minus 6 tells us 8. That's all we need to know. Another thing on this slide is how big is the nucleus? Oftentimes we wonder just how small the nucleus is. It goes back to Rutherford with that gold film experiment. He was able to determine the size of the nucleus very accurately with that gold film experiment. He was able to tell the size of the nucleus because he could tell the difference. If he kept increasing the energy of the alpha particles, suddenly the collisions would change their nature. And so he was able to determine how much energy it was taking for it to hit the nucleus, and from that was able to determine the size of the nucleus. So the radius of the nucleus, it's a spherical ball, is 1.2 femtometers times the atomic number, or excuse me, not atomic number, atomic mass, the number of protons plus neutrons raised to the 1/3 power. So if you have a hydrogen atom, hydrogen has A equal to 1. So the size of the nucleus of a hydrogen atom is a radius of 1.2 femtometers. Let's go to uranium. Uranium has, let's go 238. Uranium is either 238 or 235 for the 2 commonly occurring isotopes. 238. Well, if you take 238 raised to the 1/3 power, what do you get? Yeah, how much? 8 point something? 8 times A is 64 times A. I like that Corso does math in his head. I appreciate that. That it never be forgotten. So I'm going with Corso. What do you get a number? 238. Of course so. 6.2. Okay, so the radius of uranium is about 6.2 times the radius of hydrogen. Yes, it's multiplied by 1.2 femtometers, but I was just factoring that out. So you think about that, the radius of uranium, what our most massive naturally occurring element, is only about 6 times the radius of hydrogen. The size of the nuclei are all very tiny. Now that's talking about the nucleus, it's not talking about the electron cloud. But it's kind of interesting to note just how small the nuclei are, even for the large atoms. Now, when we talk about decay, radioactive decay, you're going from an unstable configuration to a more stable configuration. And so, just like, I won't do this. If I take this and drop it, it would fall down to a more stable situation, a lower potential energy situation. That's what's happening with radioactive decay. But just like if I dropped her calculator, there would have been some energy dissipated, right? The energy difference has to go somewhere because first law of thermodynamics, energy cannot be created or destroyed. So the energy has to go somewhere. So we have the energy of the parent and the energy of the child, the daughter as we call it, because we use gender-specific terms here. And we would say the change in energy is equal to the energy of the parent minus the energy of the child. Where's that change in energy going to go? Well, it's going to go into something that comes out. And so we call this here the disintegration energy, Q. So Q is equal to disintegration energy. And you guys have probably all studied this. If a reaction is going to naturally occur, what is that going to tell you about the disintegration energy? That's very low. Think about chemistry. What happens if you have a naturally occurring reaction? We use the words exothermic and endothermic here. It's naturally occurring, it's going to be exothermic. That means it's going to be giving off energy. And so the Q, the disintegration energy, is going to be positive if it's naturally occurring, because it'll be exothermic for naturally occurring. Endothermic, you have to put in energy to make it happen. So only things with a positive disintegration energy are going to naturally occur. The only way to make things occur with a negative disintegration energy is to force it. So how do we calculate this? Well, energy is mc squared, so mass of the parent c squared minus mass of the child or daughter c squared, which is this equation down here. Now you start to wonder. You've learned enough in chemistry to know that the number of protons and neutrons on one side is going to have to be equal to the number of protons and neutrons on the other. Right? In chemistry, you weren't redistributing them. You just said the number of atom A's on the left side has to equal the number of atom A's on the right side. The number of electrons on the left side has to equal the number of electrons on the right side if you're dealing with the ionization situation. Well, here it becomes a little tricky because the mass of a proton is not just the mass of a proton. It's not a simple thing. The mass of a naked proton is one thing. The mass of a proton in a helium atom is a different value. How many people knew that the mass of a proton is different in a helium atom than it is if it's by itself? One person. That is the key to nuclear physics. With nuclear physics, you're having mass changes. Here's a question and then a graph. Let me just go straight to the graph. That would be the only clicker question. We're just not going to do it because we only have 1 minute. Here's the mass of a proton, a neutron, and an electron if they're by themselves. So mass of a proton, 1.67262 times 10 to the minus 27 kilograms, or 1.007276 atomic mass units, or the units we really like to use, 938.27 MeV per c squared. Why do I like this one? Because if I multiply it by c squared, I have the energy. Neutron, just slightly higher. The electron, we don't really care. This here is the definition of one atomic mass unit. One atomic mass unit is defined as 1 gram divided by Avogadro's number. A lot of people don't realize that, but that's what the atomic mass unit is. It's 1 gram divided by Avogadro's number. So it's a specific amount of grams or a specific MeV per c squared. This here will be a very common conversion factor. I didn't give you homework for Wednesday. because, yeah, we don't have enough new material. I mean, I've got the equation shown here, but we didn't do a single example of this. So the next homework will be on Friday when we get new material. Have a great day. I'll see you all tomorrow.